the dimension that we are providing for our concrete slab section. Assuming this is the section through the slab, and we have these as the reinforcement at the tension zone. We are saying that our slab is going to have an overall depth of 150 millimeters. And our depth to the center of our reinforcement, which is our D effective, would have a value of 119 millimeters. So then at this point, we finished with our initial dimensioning of our beam, which is the second step after setting out our design parameters. Now, once we finish with our initial dimension, we then move ahead to estimate the amount of load that our slab is supposed to carry. Now, in estimating for our load, we therefore consider the type of loadings that our building will be subjected to. Basically, for a floor slab, the type of loads that the floor slab would have to resist is the dead load and the imposed load, since floor slabs are usually not subject to wind loading. So then we'll consider our dead loads. And for our dead loads, the elements that we'll consider to constitute our dead loads will include the self-weight of the slab itself, the finishes that we give to the slab, the partitions that the slab might be carrying, and the fixtures and fittings. This includes our lighting fittings, our ceiling fans, our air conditions, and any other fittings that might be suspended from the floor slab. Now, in estimating for the load of these elements, we usually calculate for the weight of the elements. And from basic physics, we know that the weight of an element is given by the density of the element multiplied by the volume of the element multiplied by the acceleration due to gravity. Once you're able to multiply the density by the volume by the acceleration due to gravity, then you're able to get the weight of the element. Now, in determining the weight of our element, we are going to make reference to the BS648, which has set out the various densities of various building elements. We'll only use the section that has to deal with concrete to illustrate whatever we have to do here. Now, the section that has the density for concrete has been provided for our view. And under the concrete section, the densities has been provided depending on the type of aggregate that has been used for the concrete. So we have the density of aerated concrete, we have the density of brick aggregate concrete, we have the density of natural aggregate concrete, and the density of lightweight aggregate concrete. Now, because in our situation, we normally make use of granite, which is a natural aggregate, we are going to rely on the density of the natural aggregate as our density that we are going to use to determine the self-weight of the floor slab or the self-weight of the panels that we are designing for. So then, per the provisions of the code or the BS648, we've been told that our density is equal to 2,307 kilograms per meter cube. Our density has been given as 2,307 kilograms per meter cube. Now, usually in designing for a floor slab, we usually design for per meter span. And the loadings that are usually imposed on a floor slab is the load per unit area. So then we come and calculate the volume of a per unit area of a floor slab, or the volume of the per unit area of the floor slab that we are designing for. So assumedly, if we have this as our floor slab, the per unit area volume will comprise the per unit area of our panel will comprise a floor area of 1 meter by 1 meter multiplied by a depth of 0.15 meter. Since the total depth of our floor slab that we used was equals to 150 millimeters. So then our volume, or the volume of our panel, or the volume of our concrete would be equal to 1 by 1 by 0.15. Now the acceleration due to gravity, as we all know, is equal to 9.8 meters per second squared. In which case, the final weight of our concrete will now be equals to 307, which is the density, multiplied by 1 by 1 by 0.15 multiplied by the acceleration due to gravity, which in our case is being taken as 9.8. Now this gives us a total weight of our slab, which is equal to 3391.23 newtons, which translates into 3.391 kilonewtons per 3.391 kilonewtons. So then if I pick a meter volume of the panel that I'm designing for, that meter volume has a weight of 3.39 kilonewtons. But then usually when it comes to the design of slabs, in the design of floor slabs, the design loads are usually left in kilonewtons per meter squared, or loads per meter. So whatever value we have here has to be divided by the floor area. And for our floor area, because we're considering 1 meter span or 1 meter floor area, our design or our characteristic load would be equal to, because we're considering a 1 meter area, our characteristic load will be equal to a self weight would be equal to the 3.391 kilonewtons multiplied by the 1 meter squared, which would still give us 3.391 kilonewton per meter squared. So then that becomes the self weight of our floor slab per meter squared. So then if we take our self weight of the floor slab, we have it as 3.391 kilonewtons per meter squared. Now the same procedure is going through to decide or to determine the weight of our finishes, our partitions, and our fixtures and fittings. So then for our partition, having gone through the same thing, we realize that one to be 1.362 kilonewtons per meter squared. The partition was 2.035 kilonewtons per meter squared. And for our fixtures and fittings, that gave us a load value of 0.765 kilonewtons per meter squared. Now, having arrived at the individual loads for all of the elements being considered under the dead load, everything is now summed together to get our total dead load. So once we arrive at the individual weight for the total and for all the elements, everything is summed out, and that gives us our total dead load. And in our case, we had that one to be equal to 7.553 kilonewtons per meter squared. Now, having gotten our dead load, we now move ahead and calculate or determine the amount of imposed load our slab is supposed to carry. Now, when it comes to determining the amount of imposed load that the slab is supposed to carry, the BS6399 gives us minimum loads that can be used depending on the type of building that is being considered. So then, depending on the type of building being considered, if you look through the BS6399, it gives the minimum type of loadings that can be employed or that can be applied to any structural building, or that can be applied to any building, depending on the purpose for which the building is being used for. Now, because the building that we are designing for is a residential building, we'll just extract the portion that only pertains to domestic and residential activities. Now, as I said before, when it comes to determining the loads for floor slab design, we usually determine it, or we leave it in the load per area form. So then, for our floor slab, or for the imposed load of our floor slab, we'll consider the uniformly distributed load. And according to the table, it says that all usage within a self-contained single-family dwelling unit, communal areas of blocks, flats with limited use, for communal areas in a block, in other blocks or flats, we can have the minimum imposed load to be used is 1.5 kilonewtons per meter squared. So then we'll move ahead and adapt this 1.5 kilonewtons per meter squared as specified by the BS code. In which case our imposed load or the load that we are going to impose on our building now becomes 1.50 kilonewtons per millimeter squared. Now, having arrived at our dead load and our imposed load, we are now supposed to determine our design loads as we learned in the unit 1. So then we go to our partial factor of safety table that we saw in the unit 1, and we come and factor our loads as we have decided for, or as we have calculated for. So then for our design loads, our partial safety factors in an adverse condition, because all of these loads that we've calculated for are all acting in the same direction. So then their effects are aggregated. Once the effects are aggregated, they give a critical condition. That is how come we are making use of the adverse partial safety factors, in which case we have the 1.4 GK plus 1.6 QK, where the GK stands for our dead loads and the QK stands for our imposed loads. So then for our partial safety factors, therefore for our design loads, we have it to be 1.4 multiplied by 7.553 plus 1.6 multiplied by 1.5, which gives us 10.5742 plus 2.4, and ultimately gives us a design load of 12.79 kilonewtons per meter squared. And what this means is that if I pick per meter squared of the floor slab we are designing for, it is supposed to resist a distributed load of 12.97 kilonewtons. Every square meter of the floor slab is supposed to resist a distributed load of 12.9 kilonewtons per meter. So then this is the load that we are imposing on our building, or this is the load that we are anticipating our building is supposed to carry. The maximum beyond which no other load should be. As we went through the unit 1, we learned that our characteristic load is the load beyond which not more than 95% of the loads the building should support has to go beyond. So then this, having been factored, now gives us our design load as 12.97. Now that we've been able to estimate the load that our building is supposed to carry, we now move ahead to analyze our floor slab to see the amount of movement and shears that would be induced in our floor slab as a result of the loads that is being imposed on it. So then we move on to look at our moment and our shear analysis. Again, going back to our design manual, which is the BS8110, it makes available a table that can be used to determine the moment and the shear in the one-way slab and the two-way slab. The table we have in front of us is the table that is used to determine the amount of moment that would occur with being a one-way slab, and it divides it depending on the number of spans and the position at which you would want to determine your moments. Now, assuming we have this as our floor slab, and it's being supported on beams, if we take the first column of our table, the first column talks about the type of analysis that we hope to do. That is either a moment analysis or a shear analysis. The second column in the table talks about the type of end support or slab connection. It talks about the type of end support or slab connection. And under that one, there are two types. You have the simple support or simple connection and the continuous support or connection. The simple support is where the slab terminates on the support point. The simple support is where the slab terminates on the support point and doesn't continue beyond the support point. So if you are looking at the illustration that we have over here, if we look at the illustration that we have on the board, it is a slab being carried by 1, 2, 3, 4, 5 beams. When we consider the end condition at A, you realize that the slab ends exactly on the support point A. So then in that condition, the slab is simply, or it has a simple connection at end support A. It doesn't continue beyond. On the other hand, when we come to our support point E, the slab goes beyond the support point B. So that in an event where you are designing a slab that goes beyond or that overhangs the last support, then for your end support or end conditions, you consider the column that has been headed continuous. But if the slab terminates exactly at the end beam, then we'll consider the column that has been listed or that has been headed simple support. Now, moving on from there, if you take the simple support, it has two columns under the simple support. We have the outer support and the near middle of end span. The outer support is looking at the analysis that will occur at the support point itself. It's considering the analysis that will occur at the support point itself. And because it's being assumed to be simply supported at that end, we have our moment value there being equal to what? 0. Why? Because at that end, it's assumed that the connection there is simply supported. And for a simple support, we know that the moment at that end is always equal to 0. Now, for the near middle of end span, is looking at the analysis that will be conducted near to the middle of the last span, at the mid portion of the last span. That is what the code is referring to as the near middle of end span. And at that point, you are being told that our moment value there is equal to 0.86 multiplied by FL, where F is our total design load and L is the effective span of the panel. Now, if we consider our end support, for the end support, if we consider the continuous column or the column headed with the continuous, it says that at the outer support, our moment is equal to 0.04 FL. Why? Because at that point, my slab continues over. And once it continues over, there's supposed to be a moment that would occur at this point. So then at the outer support for a continuous column or for a continuous slab, it is making reference to the analysis that would occur at this side. And for that one, we are being told that for our moment, it's going to be a negative moment with a value of 0.04 multiplied by our total design ultimate load, and the effective span. And for the near middle of end span, that one is also making reference to the analysis of the type of moment or shear that would occur at the mid span of the end span. The end span beyond which our support end, or the span just before our last support point. Whatever analysis would occur at this point is what the code is referring to as the near middle of end span. Now, having finished with our end support and slab conditions, we now move to our first interior support. And the first interior support for a one-way slab is making reference to the first support that you come across having moved away from your end support. So then we'll be considering our support point B and our support point D. These two qualify for what? Our end. These two qualify for our support at the first interior, or this qualifies as our first interior support. And at our first interior support, you are being told by the BS code that our moment would be equal to 0.086 FL, or 0.086 multiplied by our total design ultimate load and by our effective span. Now, moving on from our first interior support, the next point of analysis would be at our middle of interior span. Now, once we exit our two end spans, or once we finish dealing with our two end spans, any span that is found in between the two end spans, any span found in between the two end spans, or the middle of any span in between the two end spans, is what the code is referring to as near middle of interior span. So the midpoint of our span DC and the midpoint of our span CB qualifies for the near middle of, or the middle interior span. So then our midspan of BC and our midspan of CD is what is being referred to as our middle interior span. Then after our first interior support, any other support that is located in between the first interior support from both sides is referred to as the interior support. Any support indicated or that can be found in between the two first interior support is what is being referred to as the interior support. So then, if we are going back again, we have our support A and E qualifying for our end support or slab connection. When it comes to the outer support, you are making reference to our support at A and our support at E. When it comes to our first interior support, we are making reference to our support at B and our support at D. And for our interior support, is making reference to our support at C and any other support that might have been found between C and D. Now, for this one, because we have only 5 supports, that is how come we have our end supports being A and E, then our first interior being B and C, then our interior support being D. Assuming we had more than 5 supports, then it means that having taken away the first 2 and the last 2, any other support that is found in between them is referred to as an interior support. So then this table is used to analyze our one-way slabs, and it helps us to determine the amount of movement in the slab and the amount of shear in the slab. So then if you go to the shear analysis, it tells us that for a simple support, the shear at the simple support is equal to 0.4 multiplied by our ultimate design load. Then for the continuous support, the shear at that point is equal to 0.46 multiplied by our design load. Then at our first interior support, we have our shear force at that point being equal to 0.6 F. And for our interiors, for any other interior support, our shear values would be equal to 0.5 of our design ultimate loadings. Now, if you critically look at the table, you realize that when it comes to the near middle of end span and at our middle interior support, our middle interior spans, the shear values there are 0. That is because if you are supposed to draw a shear force diagram for our beam system. The shear forces that would be found near to our middle or near to our midspans are mostly going to have a value which, if not zero, should be very, very close to zero. That is why when it comes to our middle spans, the BS code hasn't given any formulae or hasn't given any value for the shear forces at those points. So then this is the provision that the code has made for us to be able to analyze our one-way slabs or our one-way spanning slabs. Now, when it comes to our two-way spanning slab, this is the table that the BS code has provided for us to analyze for the moment in our two-way spanning slab. There's another table that is used for the analysis of shear when it comes to the two-way spanning slab. Now, we'll take a short while and look at what the table means or what the table entails. Now, if you go to the first column of the table, it talks about the type of panel and the moment being considered. We'll first take a look at the type of panels or what the BS code refers to as the type of panel. The first type of panel identified in the table is the interior panel. Now, an interior panel is any panel which is bordered on every side by other panels. So then if we should label our panels here as 1, 2, 3, 4, 5, 6, 7, 8, and 9. Our panel number 5 epitomizes the interior panel. That is the panel which on both sides has other panels connected to it. So then if you have a panel on whose sides there are other panels connecting to, that panel is referred to as the interior panel. So for the example that we have on the board, our panel number 5 is a typical example of an interior panel. Now, if we move on to the next row, the type of panel labeled there is the one short end discontinuous. That's the one short end discontinuous. When we are talking about one short end discontinuous, as we realized earlier, a panel has two dimensions. If you pick every panel, it has two dimensions. There is the bigger dimension and there is the smaller dimension. There is the bigger dimension and there is the smaller dimension. The one short edge discontinuous is referring to a panel that has all the other sides bordered by other panels, with the exception of one of its short ends. So out of the 4 sides of the panel, the other 3 sides are being bordered by or has other panels covering those other sides. But then one of the shorter ends or one of the shorter spans has its end being discontinuous. It doesn't continue beyond the support point. So then if we take a look at our panel number 6, for our longer sides, we realize that panel number 6 is continuous with panel number 3, and the same panel number 6 is continuous with panel number 9. Then if you consider on the shorter side, panel number 6 is connected to panel number 5. But then at the opposite side of panel number 5, on panel number 6, there is no connection. That place is disconnected. So then such a panel is being referred to as what? As a one short edge discontinuous panel, meaning that it has one of its short edges being discontinuous. Now, for the diagram we have on the board, the panel number 6 and the panel number 4 are typical examples of the one short edge discontinuous. in which case they both have one of their short edges being discontinuous, whilst all the other edges are continuous into other panels. Now the next panel to look out for is the panel, or the next provision given by the code is what is referred to as the one long edge discontinuous. The other provision to look at, or the next one that we look at, is the one long edge discontinuous. And that one is making reference to a panel that has all the other panels connecting into, or it has all the sides connecting to other panels, with the exception of just one of its longer sides. So that if we take panel number 8, panel number 8 on the shorter side is connected to panel number 7 and panel number 9. But then on the longer side, it is only connected on one side to panel number 5. The other side is discontinuous. So then panel number 8 is a perfect example, or gives us a perfect example of a one long edge discontinuous, in which case all the other sides of the panel are continuous, but then only one of its long edge is discontinuous. Now from the one long edge discontinuous, we move on to the next rule, which talks about two adjacent edges being discontinuous. Now if we talk about a panel with two adjacent edges being discontinuous, it means that it has one of its long edge and one of the short end being discontinuous. It has one long edge and one short edge being discontinuous. And so if you look at the sketch that we have on the board, the panel number 3, the panel number 1, 3, 7, and 9 are typical examples of the two adjacent edges being discontinuous. In which case, out of the four edges of the panel, two of its edges are discontinuous. It has two of the edges being continuous, while the other two edges are discontinuous. So then, for our two adjacent edges being discontinuous, we have panel 3 as a typical example. Then there's panel 9, which is also another typical example. Then panel 7 also has two of its adjacent edges being discontinuous. And panel 1 as well has two of its adjacent edges being discontinuous. So then that brings us to the first end of our table. Now moving on to the second part of the table. It says that two short edges discontinuous. It talks about two short edges discontinuous. So then, as I said, if when you move to the second part of the table, it talks about two short edges being discontinuous. Now, two short edges being discontinuous is a slab or a panel that has both of its long edges being continuous or being connected to other panels, but then the two short edges are not continuous to any other panel, or they don't continue into any other panel. They end just at their support points. So then for that panel, along its longer length, it continues into another panel. Along the other longer end, it also continues into another panel. But then the two short edges are all discontinuous. Now, if we come to the sketch that we have for our first sketch, the panel number 2, 3, and 4 are all typical examples of the two-edge discontinuous panel. These are all typical examples of the two-edge discontinuous panel, whereby you have for panel 2, the long side connects into panel 1, and it again connects into panel 3. If we take panel 3, the long edge connects into panel 2 and panel 4. And for panel 4, the long edge also connects into panel 3 and panel 5. So then these panels exemplifies the two-edge or the two short-edge discontinuous panels. That's with the panel number 4 and the panel number 3 and panel number 2. So that is what is referred to as the two-edge discontinuous panel. Now from there we move on to the two long edges discontinuous panel. Two long edges discontinuous panel. Now that one we refer to the second sketch over here, and our panel number 7. Our panel number 7 exemplifies that kind of a panel, where we have the two long edges of that panel being discontinuous, but then the two short edges are continuous into panel number 6 and panel number 8. So then for the two long edges discontinuous panel, that one is referring to panel number 7, or is referring to a panel that has two of its short edges being continuous, whilst the long edges are all discontinuous. From that one, we move on to the 3-edge discontinuous, one long edge continuous. The 3-edge discontinuous, one long edge continuous. Now, for that one, we'll pick